Let's look at primitive data types in Java. All variables must be declared before use. When you declare a variable, you create a named storage location in memory for the value. This involves specifying the type of the variable and giving it a name that can be used to reference and manipulate it. Java knows how big to make our memory location based on the type we declare it to be. Java has 8 primitive data types. If you're considering taking a certification exam, get ready to take some notes. We'll divide the primitive types into 3 groups. Let's start with the primitive integer types in Java: byte, short, int, and long. There are only whole numbers in integer types. No fractions are allowed. I like to think of integer types as different sized Starbucks coffee cups: tall, grande, venti, and trenta. All of them will do the job. It just depends on how much you need. The first integer type is a byte. It's 8 bits, or 1 byte, and it can contain data ranging from -128 to +127. Short is the next type. It's 16 bits, or 2 bytes in length, and has a range of -32,768 to 32,767 inclusive. Next are integers, abbreviated as int. They're 32 bits, or 4 bytes in length, and the numeric range they can represent is from just under -2 billion to just over 2 billion. The final integer type is called long. It's 64 bits, or 8 bytes in length, and it ranges from approximately -9.2 quintillion to +9.2 quintillion. The next group is floating point types. Numbers containing fractional components, such as pi, are floating point numbers. There are 2 floating point types in Java: float and double. Floats are 32 bits, or 4 bytes in length, while doubles are twice that, 64 bits, or 8 bytes. They can be used to hold positive or negative fractional numbers. And the last group has 2 members as well: Boolean and char. Boolean contains only the values true and false and nothing else. An application uses Boolean for conditional logic, making decisions, and controlling the logic flow. The Java language specification doesn't say how much memory a Boolean must consume. It's platform dependent. The char or char data type is used to represent a single character. It's a 16-bit or 2-byte unsigned integer type that can store any Unicode character, allowing for the representation of a wide range of characters, including letters, digits, symbols, and special characters from all over the world. Let's look at the primitive data types in action. We're inside a main method in IntelliJ. By now you should be familiar with creating a simple project like this. Variable declaration looks like this: int myInt, where int is our data type and myInt is the variable name. Declaring a variable in a program means giving it a name and a type. To initialize a variable is to assign it to an initial value like this: myInt equals 25. The variables we're declaring and creating inside our main method are called local variables. Local variables are only available to us within the block of code in which they're declared. Here our current scope is defined by the curly braces used to define our main method. But local variables are only accessible from the point of declaration until the end of the block. We can print the value using system.out.println after the declaration and assignment. The println method has many overloaded variations that allow us to print strings, as we've seen in our previous lessons, or a single integer, as we're doing here. There's a nice shortcut called a live template by IntelliJ, SOUT, which will save us a lot of typing, so we don't need to type out system.out.println each time we want to use it. If we run the code, we get our value of 25 as expected. Now let's try to print out the value before it's declared. We'll try to print out the value of myInt above the declaration. Notice myInt turns red, indicating an error. If we hover our mouse over the error, we get a message that says, "Cannot resolve symbol myInt," meaning the Java compiler doesn't know what myInt is because we haven't declared it in any scope just yet. Let's get rid of that code, and let's comment out the variable initialization. 2 / characters are used for single-line comments. In this case, it's an easy way to make some executable code disappear from the compiler's view for just a moment while we try some things. When we comment out the line, the myInt variable in the println statement has a red line under it. If we hover our mouse, it says the variable myInt might not have been initialized. Local variables, as we see here, are not initialized for us. We must initialize them before use. There are other situations we'll see later in the course where our variables are initialized, but not here. Let's uncomment our code so it's working again. We mentioned block scope, which is specified by a pair of open and closing curly braces. We can introduce block scope at any point. Generally, we see blocks associated with classes, loops, conditional statements, methods, and so forth. But for illustrative purposes, let's add a block under our printline statement. The curly braces introduce a new block scope. It's still within the main method, however, but we're about to see some interesting behavior. Within this block scope, let's print out our myInt variable again. Notice it's not red. The variables we declare above the block are within the scope of this inner block and can be resolved, so we can print the value of myInt with no problem. If we run the code, it printed just fine. We got 25 printed twice. Now let's declare a new variable and assign it a value all in one statement. Int local int equals 99, and we'll do that in our new block. And we'll try to print it from within the same block using a printline statement. When we run the code, it prints just fine. We get our 25 from the outer block, 99 from the inner block. Now let's try to do the same thing, print the value of local int outside the boundary of the new block. And we see the problem right away. The variable name is red, and we get the same cannot resolve symbol error again. The problem is the scope of the local int variable. Where it can be seen is limited to just the inner block. Referring to it anywhere else will result in an error. We'll delete this code for now. Let's talk about naming rules in Java. Java names, and this goes for variables, classes, methods, anything you can assign a name, can consist of letters, both upper and lower case, digits 0 through 9, underscores, and dollar signs. Names cannot begin with digits, but can begin with any of the other characters mentioned. Java has a set of reserved words, or keywords, that have predefined meanings in the language. They cannot be used to name variables, classes, methods, and so on. Some examples we've seen so far in our lessons include things like class, public, and int, for example. If we declare a variable of type short, called myShort, and assign it a value of 5, we can assign that value to myInt with no problem. Remember, shorts consume 16 bits, while ints consume 32 bits. This example illustrates a concept called widening conversion, also known as implicit or automatic conversion. This occurs when the value of a narrower data type is assigned to the value of a wider data type. This conversion is performed by the Java compiler without the need for explicit casting. Imagine we're pouring a smaller coffee cup, let's say a tall, into a grande cup. It will fit with no problem. Other examples of this include assigning an int to a long or a float to a double. Now let's look at the opposite situation called narrowing. If we try to assign the int to a short, myShort equals myInt, we get an error. In Java, you can't directly assign an int variable to a short variable because it may result in loss of precision or data truncation. This restriction is in place to ensure type safety and to prevent potential errors. In this case, we can't pour the contents of our grande cup into our tall cup without getting a warning, even though the grande cup may not be completely full. The narrowing conversion, also known as explicit or manual conversion, occurs when the value of a wider data type is assigned to the value of a narrower data type. This conversion requires explicit casting, as it may result in the loss of precision or range. The value is explicitly cast by wrapping the target type in parentheses. By putting the type we're assigning to between equals and the source type, in this case the integer type, we tell the compiler we're overriding the behavior and accepting the risk. The risk of being wrong when casting is precision could be lost, or you may end up with a very different result than you expect as a result of underflow or overflow error. A few more things about primitive assignment before we wrap up. Let's create a variable called myLong of type long and assign it a value of 999. No big deal, right? But there is a subtle difference here. Numeric literals, in this case 999, are considered ints by default. Since the int data type is a 32-bit signed integer, it has a more limited range compared to our long, which is a 64-bit signed integer. So why is this important? Consider this. Let's create a new long variable. Long mylong2 equals 4 billion. I'm using underscores here to improve the readability of the numbers. In this case, we can clearly see it's 4 billion, and we specified the correct number of zeros. But notice what happened. We got an error. If we hover our mouse, the message says, integer number too large. This means that the number 4 billion is an integer by default, but it's outside the range of integers. However, it's not outside the range of longs. To fix that, we add an L, either capital or lowercase, to the end, and it converts the literal to a long type, and all is well. When it comes to floats and doubles, there's a similar situation to be aware of. Let's create a variable myFloat of type float and assign it a value of 3.141. Notice we get an error. If we hover our mouse, the error says required type is float, but the provided type is double. The numeric literal here, 3.141, is considered a double by default in Java. To fix this problem, we can add an F to convert it to a float. Either an upper or lowercase f will work. If we create a variable of type double and assign it the same value, without the f, everything is fine. Booleans can take only the value of true or false. We'll have a lot more to say about them when we get into conditional logic, but for now, they're pretty boring. Bytes are also not super interesting at this point either. We can assign them values just like we would any of the other integer types, except their range is very limited. We'll have more to say about the byte type when we get to the shift operators in a later lesson. The last type we'll discuss is char. The char type is used to represent a single character from the Unicode character set. Multilingual characters, symbols, and special characters can be stored using a char. To declare and initialize a char variable, we use the char keyword, add our variable name, mychar. To initialize it, we can enclose the character literal in single quotes. We can also use escape sequences. For example, we could create a variable tabchar and assign it to the \t, the tab character, and enclose it in single quotes. Finally, we can use Unicode sequences. In Java, to specify a Unicode character, you start with the \u, followed by the appropriate number sequence. Let's look at the Greek character delta. If we create a character variable called delta and assign it the Unicode value 0394, we can now print it out using systemoutprintln. So let's go ahead and run that code. And we see below our previous test data, the Greek letter delta. All right, that's it for primitive types. If you missed any of the previous lessons, check out the playlist where you can catch up. Thanks for watching, and remember to always begin secure.